The topic that we are going to be starting with today is using variables. Variables are simply just a container. They're a way of storing information. So we need a way when we're working in a program to keep track of things. And you may have found on your first project that some things grew repetitive, where you felt like you were typing the same thing in over and over and over. And anytime you're typing in the same number or the same word or the same value time and time and time again, chances are it would be better to represent that with a variable, because then if you ever want to change what that value is, where it shows up 5, 10, 100, 1,000 times in your program, you change the value once of the variable and now it changes it everywhere inside your program. So it's a nice way of working. But at its simplest, a variable is just simply a container for storing information. And when we're working with a variable, we have to have two parts that go with it. We need to tell processing what kind of variable it is, or what type. So we have certain types or kinds of variables that we're able to work with in processing. And we're not going to take a look at all of them. We'll just take a look at a few of the ones that we'll be using most frequently, especially right now in the beginning. And then after we say, okay, this variable is going to be this kind of thing. Is it a number? Is it a word? Is it a Boolean, or a value that has two possible states, true or false? So we keep track of these things. And from there, then we are able to reference them later in our program. So we declare it by specifying what type it is, and then we need to initialize it. We give it a starting value or information. So if we had a variable keeping track of the score in a game, well, that's probably going to be a number. So then we would have to know what kind of number it is. Then we keep track of it, and then we have to assign a value to it. Well, when we start the game, our score probably starts at 0, so we would start it out at 0. So when we're putting variables into our program, most commonly we put or initialize them at the beginning of our program or at the top of our sketch. So it's really important to do that, because if we try to access a variable before we have created a spot in memory to keep track of it, we will get an error message. And if we try and then access it and it doesn't have a value, we will get an error message. So we need to initialize it or declare it and then initialize its value. So if I had a number that I was working with and I knew my score was only measured in whole numbers, 0, 1, 2, 3, 4, 5, that particular type of number is an integer. So I would tell processing it's an int, short for integer, and I could call it my score, and I could give it a value. So we declare the type, we give the variable a name, so then we are telling processing, hey, take a little chunk of your memory, set it aside for the score, and oh, by the way, I wanted to have a starting value of 0. So this would allow me to use only numbers, because I've declared that my score is a variable, but the kind of variable it is an integer, so it can only be a number. So I couldn't say my score is 0 using the word, because the word 0 is not a number, it's a word. And specifically within programming circles, it's a string, which is a collection of characters. 0 is a collection of 4 individual letter characters, Z-E-R-O. Now, when we're working with our variables, we can specify the type, specify the name, and then we use an equal sign to assign a value to something or to initialize it. And certain things may require us to use quotation marks. So if I look at my number here, numbers don't sit in quotation marks, but letters or strings will be required to be in quotation marks so that the computer knows to treat those not as a command, so not as setup here or draw, but it knows to treat those as, well, just those are letters we want to see on screen. And if we ever want to represent the space character on screen, it absolutely has to be then part of a character or a string variable type. Now there's one tiny little thing that you may notice here, that when I typed in int, I used a lowercase I, but when I typed in string, I used a capital S. Now there's a distinction between these two kinds of variables that would become more important as the semester progresses. But right now, the difference is an integer is what is referred to as a primitive data type, and string is actually referencing the string class, which then is a collection of properties and methods that we can use on characters. So a character, which would be lowercase, would be something like Z. And also notice that, as before, everything ends with a semicolon at the end of a line. So primitive data types begin with a lowercase letter. Then class types will begin with a capital, because the string class has a capital S on it. We often think of string as being a primitive data type because we use it just as a basic string the same way that we use a number, like an integer or a character. So we always think of it in that sense. So it's very common to type it in with a lowercase, but string prefers the uppercase as part of it while we work with it, because it's not a primitive data type. Now I'm thinking very optimistically here. Actually, I'll even change this in my. There's an additional number type that we will use. We have integers that we use, which are whole numbers. They do not have decimal points assigned to them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are whole numbers. But if I'm going to work with a number that has a fractional component, so 99.9999, see, you're great. I'm trying to be positive here. Positive, forward thinking. But when I have a number with a decimal point, then at that point, that type of variable type or data type will be a float. So integer, float, character, string. These are most of the base types. The final one that we are going to need will be a Boolean. A Boolean is a variable or data type that has two values, true or false. So we can assign two values to it, true and false. No more, no less. It can only be true or it can only be false. A Boolean cannot be one. A Boolean cannot be a word. It cannot be a letter. It is just simply true or it's false. And that's it. The advantage of working with Booleans, and what we will find is we use Booleans to a ridiculous amount when you start doing coding, is they allow you to then check for occurrences or check for events. So you start asking, has something happened? Has my object animated itself across the screen and hit the side of my sketch window? Has my score reached a certain value? Well, that's true or false. It has or it has not. So we're asking this as a statement. So we use Booleans as part of our questioning, our conditionals, and then we set behaviors based on that. And then we can also set Booleans as events that we look for something and then we think of it as a flag, so that we've now tripped that flag. Now we can move forward inside whatever program you've written, and we can trip another flag. We trip enough flags, and then something's going to happen. So Booleans are one of the most useful types of values that we can work with when we're doing any type of visual and interactive programming. So we will use them a lot, and you will grow accustomed to them and familiar with them, and hopefully even grow to like them a little bit. Some people just don't like them. They're put off by their black and white nature, that they're just on or just off, and they feel that, you know, the world should be gray. It's not on or off, black or white, but it's a shade of gray. Booleans are your friend when you're doing programming. So in a given program, the data types that I use most frequently will be integers, floats, strings, and Booleans. These are the most popular ones that you will use. There's a handful of other data types that you can use, but we're not going to use those anytime soon. So these four are the ones that will make up the bulk of everything that you will do for the coming weeks. Integers, floats, strings, and Boolean. Now you will notice that when I named my variables, and on my screen they're showing up as white, as I've named these variables, I have strung together multiple words. Score title, your grade, my score. And when I name them, I have these multiple word combos going together, but I use a notation referred to as Camelcase. So I have score title. I leave the first word lowercase, and then I capitalize the first letter in the second word or third word or fourth word, because otherwise when I look at it without that, we can see how it suddenly is not quite as easy to read. I can't visually just scan it and read what those words are that have been strung together, and sometimes they will start making new words before your very eyes, and then you will get even more confused as to, wait, what variable is that again? So the common technique that is used by many programmers is to use the Camelcase notation. Variables by tradition begin with a lowercase letter, and then you capitalize the first letter of the second word that you've put onto it. Now if I wanted to call it my game score, I would keep repeating that pattern. Lowercase, capitalize the first letter, capitalize the first letter. But when you do it that way, it greatly enhances the readability of your code. But this variable can be named whatever I want to name it. So I could just as easily call it Fred. And it would work just fine in my program if I called it Fred. But in my program, as I'm working with it, just give myself something to look at here. So if I am working with it and want to see what's going on, now if I say going to give Fred a value more than 0, so we can actually see something with it. Then if we direct at Fred, so if I draw a rectangle at Fred, comma 2020, when I'm looking at that really doesn't make a whole lot of sense. If I run this, it should run okay. It should draw a rectangle. Yeah, it worked. Gray background, standard rectangle filled with white, black stroke on it because I haven't changed any of the particulars. So it worked. But I'm now having a value that doesn't really make a whole lot of sense. In this instance, it might make more sense if I have an x. And if I have an x, I might even want to have a y value. I need to make it bigger, otherwise that won't show. So now I can put in an x, I can put in a y. Oh. There we go, comes up. There it is, and it draws it. So when I'm using values, it makes sense to name them in an appropriate manner so that they represent, the name ties to what that value is doing. That's going to make more sense down the road when we start building more and more complex kinds of projects. When you're using variables, the question comes up of, well, how much of your program should you be storing in a variable? There are some people who write code, and anytime they're referencing a value that they're assigning a number to, or using a number for position, for size, for quantity, they create a variable for that on the chance that they may need to reference that in more than one place in their code. So in a simple program like this, it would be just as easy not to use variables for our x and y if it's just a static fixed box. But if we had a box that's moving that we wanted to do something with, suddenly at that point we may need to think about using a variable so we can keep track of what the value of something is, so we can now change it over time. And that's really when it starts to get more fun with variables. But the key thing is data types. We'll use integers, floats, strings, and Booleans most commonly. Then use lots of variables. Get in the habit of doing that because you will find that makes your life easier. So if on my first box, instead of 20, if I know it's going to be a square, so I'll call it box size. And then I would have box size is equal to, before it was 20, now I'm going to say it's 30. So if I do that and run my project, see, there it is, now it's 30. But if I decide I want my box to be 100, if all your variables are contained at the top of your program, it's much easier to find them. Because when you start getting 1, 2, 3, 4, 5, 6, 7, 8, 900 lines of code, and you're looking for, well, where does it say the code that draws this object? And you have to go find that line of code that refers to that rectangle and putting that in. That can be a huge pain in the butt to go find that place where it references it. But if the object is tied to a variable, so it's now just the size of the box, I can just change it once, run it, there it is, now it's bigger. So it's really easy to keep track of that. Start with box size at 1. So if I run this, let's just see what it looks like, and we should see a little dot. There's my box right there. It's a little dot. Little baby box. And now, what I can say is, box size is equal to 100. Now if I run this, we'll see it got bigger. So we can see I set the value of it up here. I changed its value down here. All right. What if we set box size equal to a changing value? So we've had like our mouse X or our mouse Y. So I could use that. I'm going to use mouse Y today, because that's the kind of mood I'm in. And there it is. Ooh, look at that. Ooh. So the box redraws based on Y position. Now, if you also notice that my sketch, because I am not filling the background or redrawing the background or doing anything with it, we can see all previous boxes. So if I don't like that effect, then at that point I could just put in a simple background command of, I'll just fill it with gray for now. 128 middle gray. Now, so we can see the box is changing size based on the Y value of the mouse. Mouse Y. I'm going to go back and add back in our previous message that told us what mouse X was and change it to mouse Y. So I'm printing that out. So we can actually see the number that's being assigned to box size, so it's even that much easier to make that connection. So we can see mouse Y is 10, 50. Now my Y is 150, 200. So we can see as that value changes, so does the size of my box. Since you're so quiet. So instead of tying box size to the Y position of the mouse, I'm going to tie box size. I'll say box size, I want you to be equal to whatever you were plus 1. So the first time my draw loop is executed, box size is equal to 1. So box size is now equal to 1 plus 1. That's 2. The next frame, draw runs again. Well, box size is 2. 2 plus 1 is 3. So I guess box size is now equal to 3. And that's going to keep going and going and going and going. And pretty soon my box will take over my whole screen very quickly. If I want to slow it down a little bit, I could adjust the frame rate in the project, or I could change box size from being an integer to a float and then increase it by a fractional amount instead of a whole number amount. So these are a number of things that we could do. But first I'll just run it as is because it's fun. Watch box size, and it's growing and growing and growing and growing. And if we let it run long enough, it looks like it's done, but it's actually still growing. We just can't see it anymore. So it's growing. That's what it does. It grows by 1 every frame. So it's kind of a cool effect. So we're saying box size, I want you to be equal to box size plus 1 more. So it keeps making it bigger. So the question is, can I do this with non-rectangular objects? So I am going to now say, I'm going to use a float this time. Ellipse width. Give it a height. So it's going to start out as an ellipse size of 1. and set the x and y equal to the middle of the screen. So now we have x and y, x3 and y3 equal to 250 and 200. So some extra return so I can see it on screen. So at this point, ellipse be x3, y3, ellipse. And we have ellipse width, ellipse height. So I'm now constructing and drawing an ellipse on screen with all variable quantities. Just going to comment out the rectangles for now, just so we can focus on the ellipse. It's really useful when you are doing your programming to comment things in and out, especially so you can focus on, hey, does this new thing I just added work? And not find out that it's interfering with something else previously. So this way I can comment it out. Then I can uncomment the previous things and reintegrate everything together. But when you're doing experimental and play type programming, where you're exploring, experimenting, and playing, it's very common to have tons of code all commented out. It's much better to comment code than to delete things while you're working, because you may want a piece of code that you've typed later on during a session. If you comment it, it's still there. If you delete it, then you have to recreate it. So if I run this, currently I should see a dot. And I get a dot in the middle, and it doesn't do anything. But now if I say ellipse width is equal to ellipse width plus 1, ellipse height is equal to ellipse height times 1.01. Adding a number just adds so it gets one bigger. So it started at 1, then it's 2, then it's 3, then it's 4. If we're multiplying it by 1%, we're probably going to see a slightly different response, and we will eventually get an oval-shaped object. And that's part of the fun. So we can see it filled it in. And we can see how in the beginning the width grew faster than the height. And then once the number got big enough, then the height started growing faster than the width. Which is part of, it's just fun to watch the math progression. The format that a conditional statement takes. So I'm going to type it up here more in just plain language, and then we'll worry about how to get it into code. But the format that we say is, if condition is true, then do something. So in this case, the condition that we're wondering, we want to keep making ellipse width and height get bigger as long as the width is less than the size of my screen. So we need to somehow render this statement into code. The syntax for a conditional when it's being written is if, and then we put our condition inside our parentheses. Now if you notice, it says condition is true. Well, true, and then we have the opposite of that would be false, because if something isn't true, it must be false. That's a Boolean. So we are back now kind of to the earlier topic this afternoon of talking about and using a Boolean. So if this condition, and then we put, well, so if condition, curly brace, then we say do something, and then closing curly brace. Now if you'll notice, we have an opening curly brace and a closing curly brace to my draw loop. Now my condition is an open curly brace and a closing curly brace. This reinforces why it's really important to maintain the proper indents in your coding, because when you have curly braces inside of curly braces, if you don't maintain your indents, it becomes hard to figure out what belongs with what, and who belongs with who, and who's friends and who's not. So to avoid all of those squabbles with your lines of code, maintain your indents. You will be much happier, and I will be much happier when I have to read your coding. So please do whatever you can to maintain those indents. So if a condition is true, then do something. Well, the condition we care about is if ellipse width is less than, well, the size of my screen is 500. So if ellipse width is less than 500, then we want to make ellipse width bigger and ellipse height bigger. So I'm going to take these two lines and we'll put them down here. So I've commented out the previous one. So I say draw an ellipse. If ellipse width is less than 500, make ellipse width bigger and make ellipse height bigger. And if ellipse width is now equal to 500 or greater than 500, though there's nothing that could allow that to happen, but once it's equal to or greater than 500, ellipse width is no longer less than 500, so that's no longer true, so it won't do what's inside my curly braces. That is how a conditional statement works. So when this statement is true, it will do what follows. Otherwise, it moves on. That is how that structure works. We run it. You can see it's growing and growing and growing and growing. And boom. Then it stopped. Like magic. When you get things to visually change on screen and then do something that you want to have happen and it actually works, it kind of feels like magic sometimes. When you have an if statement, there are a few things we can do with an if statement that we haven't really talked about yet that we will go into a little bit more. It will be really important that you read through Chapter 5 in your book on conditionals, because it is going to be covering things that we just won't have time to really talk about in more detail about some things with conditionals. So it's really, you really need to read that chapter. I mean, chapters 1 through 8 or 9 are just so critical to everything we'll be doing this semester. So it's really important that even if you have to read the electronic book and suck it up and do it over the paper one, even though paper one's nicer to read, I know we're all sad, but so please. But with conditionals, we can say if this is true. Well, the opposite of this is if we're less than 500. Well, let's go to a smaller number first. I'm going to say 200. So if ellipse width is less than 200, let's do that. But I do have an option where then I can say else. So I can say if this else I want it to do something else on this line here. So that something else could be I'm going to do these two things but reverse them a little bit. But so I will take this one and times it now by a number. Yep. So we'll find that when it's less, it does this, and then when it'll hit that point, and suddenly it will start doing this. So we should see a difference in behavior. So it changed a little bit.
It's not what mine did.
And that wasn't quite dramatic enough, so I'm going to swap it out a little bit. So once it hits 200, then we should see it grows quickly. But the reason I knocked this down to 200, besides else statements, we can have an else if statement. And we can say else if ellipse width is less than, say, 300. So it's only going to continue for a little while, and then it will stop again. It's 200, and then it stopped. So we can see, though, with a conditional, we can keep going, and we can now keep going and going. If we read through this, we'll see where it says, while the ellipse width is less than 200, it changes the width and height by these values. Else, if the ellipse width is less than 300, it's going to do these values. And once we've hit 300, then it's going to use this statement here and set my fill color to red. So if I run it, we'll see, and we'll go through, hits 200, then it grows up, and then it gets big, and then it pops and becomes red. So that works, but it'll be more fun if we actually then, instead of using red, introduce something that I want to get in the mix before too long, because it's just fun, and that's the concept of random. Random is just the super awesome, cool programming thing of let's give ourselves a random number. Say, I want a random number between 1 and 100, and you say, great, okay, 63. There you go, it's a number between 1 and 100. If I say I want a number between 1 and 100, if you give me -10, I'm like, nope, wrong, not going to work. Between 1 and 100. So processing has a built-in random number system. And I can just simply say random, and then I say I want it to be between 1 and 100. So there you go, 1 and 100. And it will give me that random value. Now in this instance, I'm just saying random 100, but I'm making the number, but I'm not assigning it to anything. So that doesn't really work very well there. But if I wanted to say, I want my red component to be a random number out of 255. I want my green to be random out of 255. And my blue to be a random out of 255. What that will do is that will now generate a random value between 0 and 255 for the red, the green, and the blue colors, giving me this ridiculous strobing effect that will possibly induce seizures when we hit play. So we first go to 200, then we stretch up to there, and now we can see we're getting the seizure effect occurring on screen. If we want more control over that, we can change the value of the random so it might not be out of 255, because that's now giving us every possible color combination. If I want to skew it so that it's just giving me random reds and a little bit of green, or if I want it between red and yellow and almost no blue component, that means I'm going to get, because red and green turned all the way on gives me yellow. So I'm going to, between red, green, and yellow, very little blue showing up here once it hits my value. The hard part is now we have to wait. So we can see we're getting kind of red, green, yellow, but no real blues showing up in the mix except as after image. So we can finesse this a little bit. Can get a darker color. We'll get darker versions of red now because we have a little bit of green, a little bit of blue, and now we're getting these dark reds. So you can play with it. So random will take one or two values between 1 and whatever the top end is, but random can also be specified with two numbers, a minimum and a maximum, which is super cool in my book. So if I wanted to have it to be a range of 125, 255, that would be light, so red almost all the way on. And then if we turn green almost all the way on to all the way on, and blue almost all the way on to all the way on. There we go. So we can see random can take two values as easily as it took one. It's hard exercising patience. So we're now getting a very light color. Green and blue are turned almost all the way on. Now if you're trying to remember what your colors are, you can always use the color selector from processing, and you can see, okay, well, if I'm at this color and this color, we can see red, green, and blue. So we can figure out the range as you drag through here, looking at those RGB values, and go, okay, well, if I wanted lighter colors, I need higher numbers, darker colors, lower numbers, and then I can skew it so you can see that more red to more gray. If your three numbers are about the same, you'll get a lot of grays. If one number varies more, you'll get more of that color range. So you can kind of work on doing random colors, but within a range of color as well. If you say if, and then you have your condition, and then you have a curly brace. After your condition, do not put a semicolon. The semicolon says we are done with that line of code. So then you have this extra curly brace floating here. It doesn't know what to do with everything after. It gets all wonked and confused. It doesn't happen too often after the if, but by the time you get to the curly brace, else if, and then you do it, I saw two that put their semicolon right there, which then causes it to break. So just make sure you don't do that. It's also important that don't put your next curly brace too many lines down or anything like that, or your else if, and then you start separating things onto new lines. White space generally doesn't matter, but it kind of does sometimes. And inside conditionals, it gets more particular. So watch out for that. The next part is we're going to work on making something move. We could use an ellipse. We could use a rectangle. I'm just going to use a box. It's not going to be perfect movement here, but at least it gives us a starting point, and we're going to add a little bit of physics into it because it's fun when things actually look like they're behaving based on the physical world here. So with that, I am going to need a couple values first. So if I have a single object, I'm just going to have an x, a y, and then because I'm using a box. Now width is a reserved word, so I probably don't want to use that as my variable name. I could call it box width, but I will just use w, h for height. So those should be somewhat self-explanatory. And I can have a speed. In this instance, I'm going to use the speed y because you may choose on your homework to have a speed x. So then you could code your project with both the speed x and the speed y. So I could call it speed because I'm only going to be programming things to move in one direction, but if you want to, you could do that. And then I will have gravity as part of it. So these are all now values that I've put in. You may notice this time I did not give them initial values yet. I declared them. So I told processing, hey, hold aside a little bit of memory so then we can work with these a little bit later. Now inside my setup, I'm going to say my x, my horizontal position, and I'll start out with, is going to be, I'll just put myself in the middle, and my y is going to be in the middle. Before I do that, I probably, out of good practice, should have set the size of my project. I'll just do this at 500 by 500. When you're building your homework, you can make your project whatever size you want. I don't really care. But do make it, if you make it so it fits a giant monitor, know that I don't have a giant monitor to play it back on when I play it here, so be considerate that way. So try and keep it down to a reasonable size, and then we'll be good with that. So then I have my x, I have my y, and then my width, I'll set that equal to 20, height equal to 20. So I have a little box going on here. Now one of the things that I've done is I defined or declared my variables, and now I'm initializing them in my setup. This is a good practice to get into. You declare all of your variables, but then you give them initial values inside functions, because then it makes more sense as our programs will grow increasingly more complex. And you'll start to understand the benefit of doing so. So if you get in the habit of doing that, I think you're going to just be a little bit happier. And now I need my speed y. And we'll set my speed y equal to, give it a speed of 5. That's a nice, comfy speed. I might want to start out a different amount. We'll see if that's decent or not. And set gravity equal to a very small amount. So gravity is going to be small. Now this is not a scientifically accurate physics simulation or interaction that I'll be building here. This is purely for visual programming's sake. So I've now set all of my initial values. Now it's time to do something with them. So at this point, what I can say is I will draw a rect at x and y and width and height. And notice how when I use values like x, y, w, h, it makes it really easy to say, all right, now let's draw my rectangle. Now at this point, what I can do is say, I'll set y equal to y plus, y is equal to with my speed y. And then I'm going to say speed y. Actually, before I do that, we'll just run this and see what happens, and then we'll add some more into it so we see how it's all coming together. And we can see we hit the bottom. Oops. Didn't mean to do that. Actually, I knew exactly what would happen. So I don't get that kind of trail. I will fill the background with white. And then I will fill my box with red. Okay, so I'm filling the box, clearing the background. If we run this, we'll see drops through, and we create our out. And now it's gone. It's still falling. We can't see it, but it's still falling. Now what we can do, if we notice that we're taking and we're adding in speed y is 5. When I hit the bottom, I want to go back up. I want to bounce. So really what I'm saying is if y is greater than 500, which is the size of my project, so if y is greater than 500, watch this, speed y is equal to speed y times, and this is the cool part, -1. So when we take a number and multiply it by -1, what was positive becomes negative. But if the number is a negative number and we multiply it by -1, it becomes positive. So if we take a value and multiply it by -1, we change its sign. So positive to negative or negative to positive. It's a super cool programming trick that's used in a lot of game and interactive programming. Multiply by -1 to flip the number. It's super fun. So now, when I run it, we will see it goes down and, ooh, bounced up. Uh-oh. And suddenly we floated away. But that's really easy to take care of. And this is something that your book goes into a little bit more detail. But what we can do in our conditional, because I could write it out and say, else if y is less than 0, just paste that in. So we can say else if y is less than 0, speed y, so invert it again. So we can do it like that. That's a very verbose way. It's not very elegant, but it will work quite handily. And we'll see now we create this kind of bouncing object.
It's like Pong.
It's like Pong, but going up and down. Now, if you notice this box is moving at a consistent rate, it's not slowing up, it's not speeding up. So slowing down, speeding up, it's just maintaining a constant velocity because it's only being affected by speed y, and speed y is never changing. So what needs to happen here then is we need to then modify speed y by gravity, bringing gravity back into the mix, and then we can make something cool happen with it. And we also won't need any of this extra stuff here. So I'm going to just comment all of this out. There. And before we do that, we'll just go right up here and say speed y plus, whoops, sorry, is equal to speed y plus gravity. So we can see how it's bouncing. If we watch, you'll notice that Well, gravity sucks us down. We're still having a little problem in terms of we're not being reduced at all. So we might want to modify it a little bit. Instead of multiplying by -1, which does a straight reverse, and this is where we need to play with the numbers a little bit to find out what is the ideal amount for the animation. So you can see now each bounce, it's a little bit less, a little bit less, a little bit less. And eventually I'll hit the point where it starts twitching on the ground, but that's a different problem that we want to solve. You can see and now it's twitchy at the bottom. But what we could do is we could say if it's greater than this, but then we can also put a speed limit in that says, well, when the speed down is, getting down to this kind of small little amount, we just kill it and make it 0 versus having it kind of get all twitchy. Now also notice where I said 500, that's the size of my screen. My box is being drawn at, it's 20 high. So we could even do 500, because what we really care about is not 500, we care about 500 minus the height of the box. Again, notice using a variable versus hard coding that in. I could hard code in 480, but if I change the size of my box, now 480 is wrong. That's why we want to use the H. And we'll now notice the box doesn't go off screen when it bounces, but is actually hitting the bottom. Again, these are imperfect physics simulations. But now, if you think about this, you can make something move, but you could also check when it hits the bottom, bounce it up. When it hits the top, bounce it down. But if it's moving diagonally, you have a speed x and a speed y. Now when it hits the left or when it hits the right, you can be looking for those values as well. Instead of checking y, you're checking x. So now you could make something that's bouncing around on the whole screen, and if you don't apply gravity to it or suck away its energy, and it just has speed x and speed y, and you invert them when they hit any of the perimeters, you can now have something that's bouncing around freely forever. Very energetic object.